Hi, everyone. Welcome back to the second part of chapter 8. In this chapter, in this part of the chapter, we're going to focus on two important concepts. One is the concentration of solution. Another one is some unique properties of solutions. Okay, first, let's take a look at concentrations. Okay, concentration. Okay, Hans, before we even start that, I want to kind of very quickly review what we studied in the first part. Solution is what? Solution is a homogeneous mixture in which the components are physically combined together. And of course, the major component is called the solvent, and the other components are called the solute. So concentration is basically a term that describes how much solute is present or are present in a certain amount of solution. Okay, how much solutes are in there when you talk about the solution? Of course, you guys have been using concentration or concentrated or diluted terms in our daily life, I think, in many occasions. Okay, concentrated usually you mean what? Usually you mean there's a relatively good amount of solute in the solution dissolved. Or diluted solution, you mean there's a generally small amount solute dissolved in a solution, such as our orange juice, for example, concentrated orange juice or diluted one, or some alcohol, right? Like a stronger whiskey type of alcohol, they're concentrated in ethanol, and beer, wine, they're generally diluted in ethanol. So we have been having ideas about concentration in our daily lives, but in our class, we want to study a few important concentration terms that are commonly used not only in our daily life, but also in our chemical research and labs. But the bottom line is, no matter which type of concentration you are talking about, their definition is always the same. That is how much solute, okay, the amount of solute present in a certain amount of solution. Okay, we know solute is the component. Solution is all of it. So if you understand that all concentration terms are basically defined by parts per all. Parts is what? The solute. All is what? Solution. How much solute are present in a certain amount of solution? Parts per all. And if you remember that, you have no problem of memorizing all these concentration terms because they're expressed the same way, just different unit. Okay, different unit, different type of unit. Okay, so let's take a look. What are they? But again, parts per all. In this class, we're going to study two types of concentration terms. One type is called a percent concentration. Another type is called a molarity concentration. In percent, there are three subtypes. Mass percent, M stands for mass, volume percent, or mass volume percent. And we're going to study all of them. But again, okay, I want to re-emphasize, no matter which type of concentration terms, no matter percent or molarity or which type of percent, they're all the same expression. Parts, that is the solute, over what? All, that is the solution, the amount of the solution. Keep that in mind. Okay, let's take a look. What is mass percent? Okay, mass percent, again, expressed as M over M. Okay, M over M percent. It is expressed as the mass of the solute over the mass of the solution. See, mass of the solute parts over mass of the solution. Oh, and multiply by 100%. Okay, you have to keep the percent sign in the end after you multiply 100. You have to keep the percent sign in the end. Now, we know solution is all. So sometimes you can add the mass of the solute and the mass of the solvent together to get the mass of the solution. Okay, because solution is the physical combination of these two. So the mass of the solute and mass of the solvent adding together, sum up together, you can actually get the mass of solution. You can get the all. But here is the mathematical expression of mass percent. Okay, for example, this is very simple. Okay, practice an example shown here. They ask you, what is the mass percent concentration of glucose in a solution by dissolving 5.5 grams of glucose in 78.2 grams of water? Okay, you can see that after reading the question, you have to identify what these are. 5.5 grams glucose, apparently it's a solute. 78.2 grams of water, apparently is a solvent. So you add the mass of the solute and the mass of the solvent, what you got, 83.7 will be the mass of the solution. And then you use mass of the solute divided by mass of the solution multiplied by 100%. Again, keep the percent sign. You get mass percent, 6.6%. Okay, here we keep two decimals, two sig figs, because the mass of the solute is 2 sig figs. Okay, here you can see that the question, you need to identify the components. What is solvent? What is solute? Are you given the solvent or the solution directly? Here we're adding them together to get the mass of the solution. Okay, next, very quick concept check. Okay, asking if we have a mass percent of 10%, it means what? Okay, 10% means what? 10% means per 100 solution, we have 10 grams of solute. Per 100 grams of solution, we have 10 grams of solvent. That's what 10% mean, right? 10% per 100, percentage per 100. So each 100 solution, we have 10 grams of solvent. I'm sorry, solute. Now, 100 grams, let me write it down. Okay, let's write it down here. 100 grams of solution, 10 grams of solute. From here, you can tell is what? The total is 100, solute is 10. That means what? The solvent is 90, because we can add the solvent and solute to get the solution. If total is 100, solute is 10. So that means there are 90 grams of solvent. Answer is A. Okay, not 100 grams of solvent. The total is 100, but solvent is only 90. Next, percentage concentration is called volume percent. The same expression, instead of using mass over mass, we're talking about using volume over volume. Volume of the solute divided by volume of the solution, multiply 100. Keep the percent sign in the end because it is a percentage. Why do we use volume? Because if the solute is a liquid, it's easier to measure their volume instead of the mass. That's why sometimes we choose volume. Now, here, something you need to pay a special attention. That is, we know mass of the solvent and solute can add together to get the mass of the solution. But you cannot add the volume of the solvent and the solute to get the total volume. You cannot do that. Okay, only you can do this on mass, not volume. Okay, the reason is usually you add two liquids volume-wise together. The total volume will be slightly smaller than you mathematically add them together. Such as this picture showing, you have 50 mils of ethanol, 50 mils of water. If you add them together, you find the total volume is now 100, is 96.5 here. The reason is simple explanation is molecules, they have gaps between them. So the molecules fill in their gaps with each other. So the total volume is like shrinks. So again, you cannot add volume together to get the total volume. That's something different from the mass. Okay, different from the mass. Here is a quick practice asking, what is the volume percent of the solute in 30 mils of methyl alcohol, methanol, that is, this is the solute, in enough water to give you 433 5 mLs of solution. See here, they tell you the volume of the solution. Okay, they tell you the total already because we cannot add them together, get the total. So they will tell you the total. So we know the volume of the solute, 30. Okay, volume of the solute, 30. And we also know the volume of the solution, which is 435. And simply, we use the volume of the solute divided by the volume of the solution multiplied by 100. Again, keep the percent sign. Okay, keep the percent sign. The final concentration is 6.90%. We keep 3 sig figs because the amount given are 3 sig figs. Okay, very straightforward. And finally, the last percent expression is called mass volume percent, kind of like mix mash. Okay, but the same expression, like we said, mass is the mass of the solute, volume is the volume of all the solution. So you can see that it is the mass of the solute divided by the volume of the solution, parts per all, times what? 100%. Again, keep the percent sign in the end because we're still talking about percentage. Okay, mass of the solute divided by volume of the solution. But here, one thing to pay a special attention, because these two, the units are not, one is mass, one is volume. You cannot make them consistent. So you have to use specific units here. The mass, we use grams. Volume, we use milliliter. So that's something, be careful. Okay, for mass percent or volume percent, we don't need to worry about the units as long as they're consistent because the unit cancel each other. Here, they're mass over volume. The unit cannot cancel each other. So you have to keep in mind, mass use grams, volume use milliliter. Okay, volume of the solution, okay, use milliliter. So after we have studied 3 types of percent, okay, percent, mass percent, volume percent, and mass volume percent. Here's the table shows you these 3 types of concentrations and it give you a overview and what they mean, what each concentration mean. Okay, for example, 15% of mass percent means what? 15 grams of solute per 100 grams of solution. 6% volume percentage means 6 ml of methanol per 100 ml of solution. Say volume per volume. And finally, 25% of mass over volume is 25 grams per what? 100 ml of the solution. Say grams per ml. Okay, percent means per 100. Okay, 25 grams of solute, 100 ml of the solution. So that's what each concentration basically can be translated for, meaning in words. But now, if you read the meanings, okay, for example, the top one, 15 grams of sodium chloride per 100 grams of solution. It tells us what? These 2 amounts are related now. Okay, per 100 milligrams of solution and 15 grams of sodium hydroxide chloride. So that means you can actually use the concentration to create conversion factor because they're related, these 2 amounts. 15 grams of solute over total solution or total solution over 15 grams of solvent. You can see that. We always do create a conversion factor. And the same for the second and third cases. Okay, because the amount of the solute and the total amount of the solution, regardless their volume or mass, they're related. And once they're related by concentration, you can create conversion factors. That's why the purpose of here is concentration terms can be used as conversion factor to solve problems. For example, the question asks, how many grams of sodium chloride are needed to prepare 150 ml of 0.9 mass over volume sodium chloride solution? So the question gives us 150 ml of the solution. That means we know the volume of the solution. And also tells us the mass over volume percent of the solution, I mean the concentration of the solution. We know these. We know the volume of the solution. We know the concentration of the solution. But they're asking grams of the solute, right? Grams of sodium chloride. How do we solve it? Okay, remember, once you have a concentration, you can translate the concentration into what? Into wording or a conversion factor. 0.9% means what? 0.9 grams per 100 ml, because it's mass over volume percent. Okay, 0.9 grams per 100 ml. So your conversion factor is 0.9 grams per 100 ml, or 100 ml per 0.9 grams. You can do both conversion. So now you have two conversion factors. All you need is use the given unit, 150 ml, multiply the conversion factor, 0.9 grams per 100 ml. I use this one because the ml at the bottom, I can cancel ml and ml to get what? To get grams. See that? Use the given unit, always like we did before. 150 ml, multiply the conversion factor from concentration so that the given unit is the bottom to cancel. And of course, your mathematical calculation will be 150 times 0.9 grams of sodium chloride, which is 1.35 grams of sodium chloride. Okay, sodium chloride. So you can see that this exercise tells you once you have a concentration ready, that means you can translate that concentration, tell yourself what does it mean, and then translate that into conversion factors. Because a concentration relates the amount of the solute and the amount of the solution, regardless the unit. It's always these two amount related. Okay, related. Finally, the last or the second type of concentration term is one we use most of the time in scientific research in labs, called molarity. Okay, molarity expression is shown here, mole of the solute over volume or liter of the solution, in volume of the solution in liter, or liters of the solution. So you can see that the mathematical equation, even though the units are different now here, but it's still the same, like I said at the beginning multiple times. Parts per what? Per all. What is parts? The moles of the solute, not mass, not volume, but moles. We know moles is the chemical amount. Moles of the solute over what? Over liters of the solution, means volume of the solution in liter. That's mathematical expression of molarity. Of course, molarity is represented by a capital M. Okay, when you see capital M, you know it means molarity. And the unit of molarity will be mole per liter. Why? Because moles of the solute over liter of the solution. So the unit of molarity is mole per liter. Or capital M, you can use capital M. But capital M means mole per liter. All right? So here, a very quick exercise. It tells you, hey, I have 125 mLs of solution. And in the solution, there is 1 mole of sugar. Okay, you have 1 mole of sugar in 225 mLs of solution. They ask you, can you calculate molarity? We know molarity is moles of the solute over liter of the solution. Moles, 1 mole. Liter, we were given 125 milliliter. So that means you need to convert 125 milliliter to what? To liter. Okay, to liter. 125 ml, okay, 0.0. Okay, 1.5, 120.0 ml times, okay, sorry, I forgot to include here. 1 liter is 1,000 milliliter. Okay, 1,000 milliliter. That's how you convert. Okay, someone, if you forgot what is milli means, go back to chapter 2. Milli is a prefix in front of liter, equals to 10 to minus 3. That's why you put 1,000 in front of milliliter. So first is to convert a milliliter to liter, and then use the mole divided by liter. You get what? Molarity, which is 8. And the unit, do not forget, mole per liter, or you can use a capital M. Okay, capital M. Next, okay, next. The question tells us, okay, the question tells us you have a 10 molarity solution. Big M means molarity. And then they ask you, what volume of the solution do you need in order to have 2 moles of sugar? So you were given the moles of the sugar. They're asking the volume of the solution. You need what? You need to convert. What do we use to convert? Molarity. Remember we said if we have a concentration, we can translate that into wording and conversion factor. 10 molarity means what? 10 moles per liter. 10 moles of solute, which is the sugar, per what? Per a liter of the solution. So the conversion factor is 10 moles per liter, or 1 liter per 10 moles. Okay, that's what molarity means. So you use the given unit, 2 moles, multiply the conversion factor, which you list the mole in the bottom, so 1 liter per 10 mole. Because I want to cancel the moles to get what? To get liter, right? And then do the mathematical calculation in your calculator. You get 0.2 liter because mole canceled. Okay, you use the given unit mole and use concentration as a conversion factor here again. Okay, always keep in mind, concentration is something relate the amount of the solute and solvent, a solution, I'm sorry, solute and solution. So if you know the solute, which is here, you need the solution. Concentration is the best conversion factor. But keep in mind, you have to translate the concentration first and create a conversion factor and know which one to use. Here we use the one with the mole and the bottom. Okay, on the bottom. Next exercise. Okay, I want to go over all these with you and show you all types of questions that are related. Okay, this question asks, consider separate solutions of sodium hydroxide and potassium chloride made by dissolving 100 grams of each solute in 250 mL of water. Calculate the molarity of each solution. So here we're talking about 2 solutions. Okay, I'm here only demonstrating you one of them. You do the other. So I'm demonstrating you prepare sodium hydroxide. Again, you do the other, potassium chloride. They dissolve 100 grams of sodium hydroxide in what? 250 of solution, 250 mL of solution. They ask you the molarity. Remember, molarity is what? Mole per liter. So first you need to know mole. Here we're not given mole, we're giving what? Grams. So the first thing you need to do is convert the grams of sodium hydroxide to the moles of sodium hydroxide using molar mass. Grams and moles and grams use what? Molar mass. We did a lot of times in chapter 6. Okay, the molar mass of sodium hydroxide is around 40. So 1 mole per 40 grams. Grams cancel, you get a mole. So you need to convert the 100 grams with the molar mass to moles of sodium hydroxide. You can list it, or you don't need to calculate it now. You can do all the calculation all together. And then mole per liter, you need what? Also, you need liter of the solution. Again, we were given milliliter, so I multiply 1 liter over 1,000 milliliter to get the liter. Okay, to get liter. And of course, using moles divided by liter, I get what? I get the molarity. Okay, I get the molarity. So this is how you normally will calculate a molarity, because remember, solute we can calculate, we can measure in grams. We don't know moles. If we want to know mole, we have to convert grams to moles. Okay, again, use potassium chloride to do the same calculation. Can attest to if you understand these concepts. Okay. Now, I have done many practices. I want to leave. Okay, I want to leave the rest of them for you, especially this one. Okay, especially this one. They ask you, how do you prepare 200 mL of 0.8 molar of sodium hydroxide? Okay, they tell you the volume of the solution. tell you the concentration. So basically ask you what? How much solute you need. Remember, concentration is what? Relating solute and solution. They tell you 200 mL of the solution. So basically this question asks you, calculate how much solute you need, especially in grams, how much solute. Because remember, if you want to prepare a solution, the solute, which is sodium hydroxide, it's a solid. It's better to measure in grams. Okay, but we know the concentration already relates the solution to solute already. You just need to do the convert. Okay, just need to convert. Okay, I'll leave it up to you. How do we prepare? I said, you need to first figure out how many grams of sodium hydroxide is needed by doing a conversion. Okay, by doing a conversion. Now, preparing a solution, okay, in a lab, usually we use a volumetric flask, okay, which has a designated volume number. Like here, if we need 200 mL of, we have a 200 mL volumetric flask to prepare that. But many times, when we prepare a solution in the lab, we usually prepare the solution in a very high concentration and store them as a stock solution. Whenever we need it, we do a procedure called dilution. Okay, dilution to get to the concentration we need. We prepare them in high concentration and store them on shelf because they're concentrated, so we can prepare them in a small amount. Then when we need them, all we need is to add water or solvent. Most times solvent is water. Okay, add more solvent to dilute the solution to any concentration we want. And this procedure is called dilution. Okay, dilution. Calculation involves dilution as one thing, a central principle. That is, when you dilute a concentrated solution, what you're adding is what? The solvent. So that means before and after the dilution, the amount of the solute doesn't change. Before and after. You just add some solvent. See that before and after you add solvent. The color gets lighter, means what? It got diluted. But the total amount of the solute never changed. You only added water, solvent. If you understand that, you will understand this mathematical equation involving dilution. C stands for concentration, multiplied by volume. Concentration multiplied by volume normally equal to the solute. Remember, solute over volume is concentration, right? So if you use concentration multiplied by volume of the solution, you get the solute. And of course, S stock solution and diluted solution, S and D, their solute should be the same. So C of stock multiplied the volume of the stock should equal to C of the diluted solution multiplied by volume of the solution, of the diluted solution. Again, C times V, concentration times volume should equal to solute. And since solute doesn't change before and after dilute, the total amount of solute to equal. So C times V equals to C times V. That's the central rule or mathematical equation for handling dilution. For example, how do you prepare 100 ml of 0.9 saline solution? 100 ml of 0.9 saline solution from a 10% stock solution. See, if we prepare 10 as a 10%, but what we need is 0.9%. So all we need is what? Dilute that 10% to 0.9%. But how do we dilute? Remember we said the central rule, C times V. So 0.9 times V, 100 ml, should equal to 10% times V of the stock. Remember, 10% is the stock. So C times V equal to C times V. 0.9 times V of the diluted equals to 10% times V of the stock. And we have 4 variables, 3 of them are known. So all we need is to solve V stock. If you divide by 10% on both sides, you get 0.9 times 100 divided by 10%. The volume is 9 ml. Means what? Means you need 9 ml of the stock solution. And then you keep adding water to it until the total volume gets what? Gets this 100. Okay, you see, use C times V equal to C times V. You first solve, hey, I need 9 ml of the stock. Then you just simply get 9 ml of the stock solution, which is 10%. You add water until the total volume becomes 100. Then the volume, the concentration will definitely be 0.9% because we calculate it. That's how we handle dilution. Understand the solute amount does not change, and also that mathematical equation. Okay, I'll leave this one to you. Okay, I even give the keys for here, but I leave this one to you. See if you understand the simple calculation. Okay, the most important thing is you need to figure out what is original concentration, original volume. What is the diluted concentration and the diluted volume? Okay, you need to be able to identify these. I think that's the most challenging one, where you read the question, read it a few times so that you understand what these numbers mean. Then you use that concentration times V equals to concentration times V. The concentration can be percent, can be molarity, doesn't matter. As long as it's a concentration, as long as they're consistent before and after. All right, I'll leave this up to you. Again, I put the solution here. You can pause the video, cover the answer key and try it by yourself, and then take a look at the answer key. Or study the answer key, see if you understand, and then try it again without the key. Finally, in this chapter, okay, we're going to talk about some very unique properties involving solutions called colligative properties. The reason we call them colligative property, because these properties only depends on the number of solute particles present, not the identity of these particles. So all solutions can have the same property if they have the same number of particles in them. That's amazing. That's why make this unique. What's more colligative? Okay, colligative because it only depends on the number of particles. Of course, the number of particles of the solute could be molecules, could be ions, it could be atoms even. Okay, the solute could dissolve as particles. We studied that in the very early beginning of the chapter. And the property, these property would be dependent on the number of these particles. Okay, number of these particles. And because it depends on number, if you have two solutions like these two, 1 molar molarity of sugar or 1 molarity of sodium chloride, their property will be different, even they're both 1 molar. Why? Because sodium hydrochloride is ionic compound. In water, ionic compound will actually dissociate into ions. So a sodium chloride here, it contains 2 ions, sodium cation and chloride anion. So each sodium chloride actually dissociate into 2 ions. You see that? They're both 1 molar, but the amount of particles won't be the same. Sugar does not dissociate, but sodium chloride does. So the amount of particles of sodium chloride will be twice as much as the sugar solution. And because of that, their properties are actually different. That's why, again, called colligative properties. What are these properties? We're listing them here. 4 of them. The first one is vapor pressure lowering. Second one is boiling point elevation. Third one is freezing point depression. The last one is osmotic pressure. The first 3 you can actually know what they means and verbally. Okay, lower vapor pressure. higher boiling point, elevation, lower freezing point, right? And the last one, osmotic pressure, we probably haven't heard it before, we'll explain. But these are the 4 important colligated properties of solutions. Okay, the first one, let's take a look. What it is and why is that? We know solution has solvent particle in there. And the surface solvent will what? Evaporate to become gas. And that gas, we call it vapor. But for a solution, okay, because the solute particles takes the place of the solvent on the surface. You can see that the yellow ones are solute. Okay, they take the place of the solvent, so that what? Less solute particles will be on the surface to evaporate. Less solvent particles evaporate means what? The vapor pressure is lowering. Again, because the surface of the solution are taken by some of the solute particles. That's the simpler explanation. Or you can see here, the solute particles replaces some of the solvent particles at the surface, so that the solute particles interfere with the ability of the solvent to vaporize. That means compared to the pure solvent shown here, solution will have a lower vapor pressure. That's what the first property means. Lower vapor pressure of the solution than the pure solvent by itself, because less particles will evaporate due to the solute particles. Okay, due to the solute particles. Now, we know in order to boil a liquid, the vapor pressure has to reach the atmosphere pressure, right? Vapor pressure has to reach the atmosphere pressure for boiling. When you have a solution, the vapor pressure is lowered, even lowered. So it takes what? Takes higher temperature to raise it to the atmosphere pressure, for raise the vapor pressure. So basically, with a solute, because the vapor pressure is lower, it takes it harder to raise the vapor pressure to what? To the atmosphere pressure. So the boiling point is higher for solution. Okay, boiling point is higher because vapor pressure is lowered, because it takes harder to boil now. That's what boiling point elevation means. Now, usually we don't do math on this, calculation on this topic for this class, but if you're interested, if you're curious, 1 mole of particles will raise the boiling point of 1 kilogram of water by around half a degree, 0.51 degrees Celsius. That's 1 mole of solute will raise the boiling point of 1 kilogram of water by 1 degree. I'm sorry, half a degree, 0.51. I'm sorry. That's how much elevation we're talking about. The third one is called freezing point lowering, meaning solution will have lower freezing point than pure solvent. A lower freezing point than pure solvent. Okay, this one actually is applied in our daily life a lot, especially you have lived in the northern state a lot before. People add salt on what? On icing surface or during snow days. Why they add salt? Because salt will make a solution with ice and water so that the freezing point is lower. So water doesn't freeze that easy because the freezing point is lowered. We utilize that property by adding salt on the road, okay, on the walkway, so that the freezing point of the ice water mixture will be lowered. Prevent easy freezing. And also, our antifreeze is also a solution mixture of ethylene glycol and water. And because of that mixture, the freezing point is very low. So our engine doesn't freeze. Okay, the coolant doesn't freeze. Now, the reason behind this simple explanation is the solute particles prevent the solvent particles to freeze. Because in order for something to freeze, the more molecules can have a network build, like especially water. The hydrogen bonding has to build up to organize the network of solid freezing. The presence of the solute particles will prevent the formation of that solid network, so that freezing is difficult, more difficult. That's why solution freezing point is lowered. How much lowered? Usually 1 mole of solute will lower the freezing point of 1 kilogram of water by close to 2 degrees, 1.86 degree, if you're interested. Finally, osmotic pressure. In order to explain this one that we're normally not familiar with, we first have to explain a natural phenomenon called osmosis. Okay, what is osmosis? Osmosis is showing in this device. Okay, you can see that the tube contains a concentrated solution. The beaker contains a less concentrated solution, a diluted, and the open end of the tube has a semi-permeable membrane. Okay, this membrane only allows certain particles to pass, such as water, which is small particles, to pass through. The solute does not pass through. That's called a semi-permeable membrane. Okay, that's what the setup of the device. And then if you have a device like that, you will see that. Okay, you will see that the water will move in the direction. Again, only water can pass through that membrane. Water will move from the less concentrated or even pure, from less concentrated into the more concentrated one. Okay, the tube one is more concentrated. Okay, tube one is more concentrated. That is the direction of flow of the solvent. And this is called osmosis. Okay, when you separate these two solutions, concentrated and diluted, okay, with a semi-permeable membrane, then what happened is the flow direction of water will be from less concentrated to more concentrated. You can see that more concentrated tube is gonna rise up because some water gets in, right? That's called osmosis. Okay, osmosis. Now this is the macro, like a magnified view of that membrane. Okay, of membrane. In fact, water actually flow in both directions. Okay, both directions. But it is easier for water to flow from the less concentrated to the more concentrated one. So the net direction of water flow is from less concentrated one to the more concentrated one. Okay, because it's easier. The other side has more solute. Interference is the more difficult. Okay, water is actually going both directions at the membrane. Membrane does allow water to pass through, but it is easier for water to go from the less concentrated to the more concentrated, because the more concentrated has more solute, which prevent the passing of water, ability to cross the membrane. So the net direction is always to where? To the more concentrated. Now you might wonder what happens when water gets into the more concentrated. If water gets into the more concentrated is going to be what? To be diluted. And meanwhile, when water goes away from the less concentrated is going to be more concentrated, right? Think about water gets in here. The tube is going to be diluted. Meanwhile, water leaves here. The beaker here is going to be more concentrated. So one concentration decrease, another concentration increase. Eventually, what? They may be the same. That is when osmosis stops. When the concentration of both solutions separated by the semi-permeable membrane are identical, are the same now. In that case, water flows in both directions the same way. You don't see the rise of water in the tube anymore because osmosis stops. Okay, that's what happens. Okay, what happens? in osmosis. Now, finally, let's get into the concept. Because of osmosis, okay, if you separate these solutions, you will have osmosis. And if you want to go against that natural spontaneous process of osmosis, you need to apply a pressure on the concentrated solution so that you prevent the solvent to go up, to go to that direction, just to press it down. A pressure must be applied to prevent the net flow of the solvent from less concentrated to more concentrated. You have to apply for pressure to prevent that happening, to prevent osmosis happening. And that pressure is the fourth property of the solution called osmotic pressure. Okay, we explain all these to introduce the osmotic pressure. Okay, a pressure to prevent the net flow of water. Now, because osmotic pressure is a colligated property, it is depending on what? Depending on the number of particles. Okay, on a particle. So we have a term called osmolarity, the osmolarity, to compare different osmotic pressures for different solutions. Osmolarity equals to molarity. You can see that it's a combination of word, osmolarity. Okay, it's basically molarity multiply a factor called I. Molarity is the concentration, no difference like we studied before. But I is a factor. This factor determines how many particles will result for each unit of the solvent, solute, I'm sorry. How many particles will result for each unit of solute? Okay, for example, sodium chloride. This is the 1 unit, but this unit will generate how many particles? 2 sodium and chloride ions. So I equal to 2 for sodium chloride, because each sodium chloride will generate 2 units of particles, 2 particles. So osmolarity of sodium chloride needs to use the molarity of sodium chloride multiplied by 2. Okay, that's called osmolarity. Okay, osmolarity. Here, very simple. What is the osmolarity of 3 molar sodium chloride? Okay, 3 molar sodium chloride times I is 2, sodium chloride is 2. So osmolarity is what? Larity is 6 osmol. Okay, 6 osmol. That is the factor determining the osmotic pressure for sodium chloride solution. Now, speaking of osmosis, there is something biology-related concept we want to introduce you here as well briefly. Our cell membrane are also semi-permeable. That means our cell membrane normally only allows small molecules such as water to pass through freely without transporters or helper. So, because our membrane is a semi-permeable membrane of our cells, so osmosis can also happen when you place the cell at different concentration environment. If you place your cell, for example, in pure water, means much less concentrated, right? Pure water is just pure solvent. So what happened is the water will come from outside the cell into the cell. Remember, the direction of osmosis is from less concentrated to more concentrated. So water will go into the cell. Okay, into the cell. What happens is cell will what? Cell will break, explode. Hemolysis. And we call the solution, the environment that caused this water flow into the cell, a hypotonic environment. Hypotonic. On the other hand, instead of placing the cell into pure water, if we place the cell in salt solution, concentrated solution, so water will flow from less concentrated to more concentrated means flow outside of the cell, because you place the cell in a more concentrated environment. The water will leave the cell, and the cell will, of course, will what? Shrink, crenation. And that environment is called a hypertonic solution. Okay, hypotonic and hypertonic. Of course, cell is the most stable when placed in a solution, has the same concentration as this inside the cell, and we call that environment isotonic solution. Iso means the same. Here is the summary of what happens when you place the cell in different environment. And in fact, you have a lab related to this chapter, related to this topic. Of course, we're not using human cells, we're using plant cells. We're using a piece of potato to demonstrate that, whether water flow out or flow in. If water flow in, your potato will be heavier. If water flow out, your potato will be what? Will be lighter. And you can even feel it. And of course, you will weigh it, of course. But remember, when you place potato in concentrated, water will flow out, hypertonic. When you place potato in water or diluted, water will flow in the cell, hypotonic. Okay, hypotonic. And that's the logic of our lab, because the solution lab is a handout lab. Okay, I will remind you. Finally, I have a comprehensive practice here, half summarizing what we have learned, especially the calculation of solutions, of solution concentrations in the second half of the chapter. You're adding 2.6 grams of sodium chloride to enough water to make 300 mL of solution. So you were given two things: the grams of the solute, the volume of the solution to 300 mL. They ask you to calculate three things: molarity, mass volume percent, and osmolarity. Okay, they tell you sodium chloride. So I equals to 2 for sodium chloride. So these are the three concentrations. I think is a very good practice for you. Okay, ask yourself, what is molarity? What is mass over volume? Which one do we need to calculate that molarity or mass volume percent, etc. Okay, I'll leave this up to you as a practice. Again, I think I provided the key in the notes. If not, always feel free to ask me questions. That is all for chapter 8. I'll see you in our next chapter. Bye now.